Yes, it should be recording now. So the first thing we're going to do today is see how a density matrix evolves in time. That's kind of the Schrödinger picture generalization of state evolutions, right? If you have full knowledge of the state, if you know as much as you can know about the state of the system, you know the state vector, and we know how to evolve it, right? Well, we are always, in this semester, we're only thinking about Hamiltonians that don't depend explicitly on time. So if that's the case, we know that the state evolves as u psi, and u is e to the minus I h bar plus I, h bar t minus I, on h bar, yeah. Right, that's what we saw last time. Well, not last time, but we've been doing this for a long time already. And now we're going to see what happens if you have a density matrix. Because there are states, what we want to call states, that can't be right. You have mixed states, and they can't be written like this. Perhaps, let's keep an example in mind. There is a very important example of a mixed state, which is, for physics, is extremely important, which is called a Gibbs state. Well, I'm sure you've heard about Gibbs states in Theorem, probably this semester. So let's write in quantum mechanics what a Gibbs state is. And you will recognize it. So a Gibbs state, an example of a mixed state, is rho g, as you call it. I'll write as e to the minus beta h divided by the trace of it. This is called a Gibbs state. Do you recognize this state? Maybe if we write this state in an eigenstate, let's use the spectral decomposition of H and write this in the so how he acts on an eigenbasis of the Hamiltonian. Right? So this is the definition of the state. It is beautiful, written in the operator form, no basis needed. I don't have to say, well, in which basis I write. No, there is no basis. Here is the operator. Right? But we can write in a basis if you want to. Why don't we use the basis of the energy? So let's say that, well, we have to think of the energies being degenerate or not. Let's simplify our lives and imagine that there is no degeneracy. So just so you see, I just want you to recognize the state, right? But let's say you have no degeneracy, so every energy, every state has a distinct energy from any other state. So we can write, like say, let's call it EI, a basis of energy. So we can write this as, well, first of all, this is just a number. Let me call it Z. So this is just a number. I can give it the name I want to, call it Z. And here I'm going to e to the minus beta h is, I can write it e to the minus beta ei times the projector. On that energy. Now I'm sure you recognize it. Right? 1 over z e to the minus beta I times the projected energy. So this is a thermal state with temperature 1 divided by kV beta. So this is a very important type of a mixed state. It's a thermal state. So how does it evolve in time? How should it evolve in time? If it's an equilibrium state. So we have that as a test case. How should an equilibrium state evolve in time?
Is it linear?
It's an equilibrium state.
It doesn't change.
Yeah, it shouldn't change. So we can test that in this case. Notice that if I wanted to, yeah, anyway. So how do we evolve the states in time? Obviously, we can't introduce any new physics because it's fully determined. I can write And the density matrix generically, as we saw last time, you can write rho as the sum of mu of p mu mu mu. Right? But I know how to evolve this in time. So let's just use the time evolution. So as a function of time, as it evolves in time, it's a bit light, it's light abuse of notation. So this should be at t equals 0. At t equals t, this will have to be mu, p mu. This mu, I apply this operator here. And I apply this operator here. Right? If you want to find a differential equation that it obeys, we can always take the infinitesimal version of this law. So we'll take the infinitesimal, so you have rho of t equals delta t. Well, that's going to be the sum of mu, p mu, I write here as this 1 minus I h t h bar mu mu 1 plus I h delta t. H bar plus order t squared. Well, now I can recompose this. Well, this one I'll get the same object, so this is going to be the sum of mu, p mu. This, when 1 acts on 1, this is again mu mu. Now, here I've got, let's see what I've got. I've got minus I h on h bar delta t times mu mu. Right? And then I've got this one times this one. Oh, this one is, when this one acts on this one, it's the order of h delta t squared. So I throw it out. This one acts on this one. When h acts on this, I get this. Now I get this acting on h. So I get plus I h on h bar delta t. No. And mu mu h. Right? Do you agree? Plus h squared delta t squared, but delta t squared I have to ignore because I'm only going to the order, second order. So I write is I delta t on h bar. Now I put a commutator between h and mu mu. Plus order of delta t squared. Okay, so this is the same object that I had before. This I can this I can plug in inside the commutator because these p mu's are just numbers. So I found a differential equation for this, d rho dt. It's going to be, I remove this delta t minus I on h bar rho h rho. That's the differential equation for rho. I prefer, well, I wrote it as I, to make it more symmetric to what we had before, I wrote it like so. And this equation is often called the von Neumann equation. It's really just Schrödinger's equations applied to the density matrix. Now, who thinks this is known? We've seen this before. Aha, good. Your memory is partly correct, but no. This looks a lot like the Heisenberg equations of motion. Remember? Heisenberg equations of motion, for reference, this is not in the Heisenberg picture. So immediately you should know that this should not necessarily obey the Heisenberg equation of motion, because this is not the Heisenberg equation. The Heisenberg equation of motion was this. It differs by a sign. So be careful. It is very similar, but it's not the operator rho. It is not the Heisenberg equation of motion for the operator rho. Okay. Now, any questions? So let's see how this one evolves in time. So Zachary's expectation is that it shouldn't, because it's an equilibrium state. So as you move towards equilibrium, there should be a non-trivial time evolution. But once you are in equilibrium, it should stop evolving. Is this what it happens here? Let's see. What's the commutator between H and this rho G?
Should be 0.
It is 0, right? This is just an exponential of H itself. Certainly H commutes with itself. H commutes in any power of itself. So H commutes with exponential of itself. So the commutator is 0, as it should. And the rho dt is 0 for that one. Okay. So the next thing I want to do now is use this version. We could actually have done what I'm about to start doing now before. Once we had the time evolution, with this operation, with this equation, we can already do what I was going to do. I'm about to start doing. But since we had these matrices, let's do the matrices. Let's find what I'm about to do is to find the differential equation for the expectation value of a certain operator as it evolves in time. Well, I don't need to motivate that. That's a very natural thing to do, right? Because then you don't have to worry about the quantum part of this. Because if you have a differential equation for something that is not an operator, an expectation value is not an operator, you can pretend you don't have operators after all, and you can evolve things in time. But of course you're missing information. You're just getting information about the expectation value, as opposed to have information about the whole operator. If you want to offer information about the whole operator, there we go. That's what you should be doing. Right? Heisenberg equations of motion. Anyway, so let's do that. So let's find differential equation for that. So the expectation value of A was the trace of rho times A. Right? That's what. Bless you. That's what we had. That was the expectation value of that. Right? So let's see how it evolves in time. I'm going to take a d by dt, and let me put an I in each bar in front, because of this I in each bar there, and let's see what happens. Well, from this equation, I know that A will not depend on time, because this is the Schrödinger picture. So from this equation, I know that this should be the trace of the commutator between rho H and rho. Be careful with the sign. I was about to get the wrong sign again. Times A. So now I open this commutator. This is the trace. The trace of the sum is the sum of the trace. So I'm breaking this into traces. The trace of H rho A minus the trace of rho H A. But this one, I use the cyclic property of trace. Right? Remember that trace of ABC is the same as the trace of CAB. Right? So this is just the trace of rho AH. Okay, so this is just, now I I put them again, so this is just a trace of rho. I factor rho, and then I got a commutator between H and A and H. Well, but this is again just a form of trace of rho times an operator. So this is just the expectation value of the commutator AH. On that state rho. So that's our equation. Let me write it again. This is our equation, how it evolves in time. So now, if you go back to our early construction, this is formally identical to the classical equations of motion under expectation values. Right? Why? Because if you remember, recall that the direct quantization, the commutator between A and H, was just IH bar times the Poisson bracket A and H. So I can cancel IH bar, and under expectation values I have d, the ADT is the Poisson bracket. So that's the classical equation of motion. So, do you see what I'm saying, right? So this is just like the classical equation of motion under expectation values. This has a name. This result is called Ehrenfest. However it's pronounced his name. Ehrenfest theorem. So it is, and it's often abused. So let me just, so what is often stated. So, okay, what I'm saying is the following. It is a statement that what it's not. So just be careful. Like you just have to remember that the expectation value comes after everything else. You do all the operations, and then you take the expectation value. If you're careless when you're doing this, you can make a mistake because the equations of motion, for example, let it go. This is in the Poisson bracket notation, but you can also write in the canonical equation, right? The canonical version will be something like P dot, or the PDT, minus dH dq under the expectation values. Now what this is not is this. So because h of q is not this. Right? So it's not completely classical because you should take the expectation values as a last step, not the first step. So just be careful with that. So if you don't fall into that trap, you can use Ehrenfest theorems. And so that's one of the ways, transition from quantum to classical is not necessarily easy, and it's, we're going to see approximation methods, and they are very interesting. For example, well, next semester we're going to talk about approximation methods. So one of the approximation methods could be seen as an expansion in powers of h bar. So that's one possible way of understanding how the quantum to classical transition happens. But there are many interesting things that already happen at that level. For example, you get the quantization. So if you took modern physics, chances are that you saw stuff like the Sommerfeld quantization. Sometimes called Wilson, Sommerfeld, Bohr, Sommerfeld, just Sommerfeld, right? So that had to do with the action. You write the action integrals, and you said that was n times h bar. that comes about in that expression. So you understand the quantum origin of this old quantum theory. This is quite interesting. But this is one of the ways that you can think of the classical transition. So if you're only sensitive to expectation values, and it's not very easy to get, how to justify why would you would classically only be sensitive to expectation values. But it's one way of helping understand the classical transitions. Okay, great. Yeah, that's all I have planned for today, but we have time left. So if you have questions, great. If you don't, let me start introducing what we're going to do on Monday, which is quite giant. So perhaps I could start by explaining a bit of the context in which, what we're going to talk about on Monday. Yeah.
So you said to recall that the commutator A and H is equal to IH bar for some brackets A and H. How can we relate that to the expectation value?
If you write this commutator,
Do we just write
if
inside?
so if you write this commutator that, you'll get d a dt is the Poisson bracket A with H under the commutation value.
Okay, so you can just, because it's in the Poisson brackets, it's in the expectation value of the brackets, that it's fine to just replace it. And then you
Right, yeah, this is just a constant, so I can put
Okay,
it, I can put inside the expectation values, no problem. But if you remove the expectation values and forget that A is an operator, this is exactly the equation of motion, the classical equations of motion. So that's the content of Ehrenfest theory. Great question. More questions? So let me motivate what you're going to do on Monday. Monday is a big day. So what we're going to do is the following. Question. I will start with a question. And that question, obviously, I'm sure had been asked since the early days of the quantum theory. The question that I wrote here is, could the randomness of quantum mechanics be attributed to some local random variables that we don't have experimental access to? Or is the randomness of quantum mechanics something else? Is this even a scientific question? Can we decide that experimentally? I don't know about you, but it's not obvious to me that this is. Well, the spoiler, it is. As well, with a small caveat, this is a scientific question. It can be tested experimentally. But I don't know about you, but it's not obvious to me that this was going to be. So let's be very concrete. Let's say we're going to talk about angular momentum eventually. We've been delaying far too long. Perhaps I should justify why we've been delaying talking about angular momentum for so long. It is somewhat artificial, especially if you include spin. The spin comes about naturally in relativistic quantum mechanics. It is a necessity, it's a prediction of the relativistic quantum mechanics that you have spins for certain types of matter. But it's not true in non-relativistic physics. So in non-relativistic physics, we have to put a spin by hand. And that's somewhat artificial. So there is not something beautiful from top down. I can come to you and explain what spin is. I'll have to bear it by hand. If we're doing relativistic quantum mechanics, we could predict the spin. And there are nice consequences. For example, the relationship between spin and angular momentum will become evident. Because in non-relativistic physics, you don't have separate conservations. In relativistic physics, you can convert spin to orbital angular momentum and vice versa. But this never happens in non-relativistic physics. They are conserved independently. So schematically, the total angular momentum is something like the spin plus the orbital angular momentum. Both in relativistic and non-relativistic physics, J is conserved. But in non-relativistic physics, J is conserved because S is conserved and L is conserved. So they kind of detach, they decouple from each other. So that's why I haven't talked that much about the theory of spin. We operate with spin because spin is easy. We get finite dimensional systems, two-level systems, qubits, and so on and so forth. And you can understand a lot of the principles of quantum mechanics by working in a very elementary system like a spin 1/2 system. But to introduce what is a spin and so on, it will be a little bit more artificial. So that's why I've been delaying so much to do so. I want to use it as a testing ground of the theory, but anyway. So one of these experiments, let's be very concrete. You can imagine that you have a reaction like a particle level reaction. Let's say you produce a pair of particles. You produce a pair of particles here. And you know that this, for the conservation of angular momentum, the total angular momentum of the system should be 0. If the total angular momentum of the system should be 0, if I were to measure, well, the state, if you look at the Bell states, the states that I had introduced when we talked about quantum teleportation, a state like this, up, down, minus, down, up, with a normalization factor or something like this, will do the job. So the prediction of quantum mechanics is if I measure, let's see what happens if I measure the spin of the leftmost particle. Let's see, it's the first entry. Let's say I measure its spin up. So what should I do? I should project the state on to that. So I should multiply this state by the projector on, let's say it's measured spin up. So I should multiply this by this. So let me call it psi. Or B, I think this was before, right? To keep the notation consistent with our quantum teleportation. Was it before? Let me see.
10101.
Yes, it was B3. B3. So if I project this on B3, the result I get is this will give me 0, this will give me spin down. So there's no surprise whatsoever. If the spin here is up and this total spin is 0, the spin of this particle must be down. And vice versa. I could project, so, well, this is operation, so be this cross the identity. O times the identity that. The same would happen if I had identity, O times up, up. Same thing. Right? So if Bob measures a particle instead of Alice and so on, in other cases will happen. So there are correlations. There are obvious correlations and there are no surprises. Why? So how does that happen? Well, I think most people, except perhaps Niels Bohr, but probably, almost certainly, John Bell himself, would thought, well, that's simple. The particle knows. It has a program. Say at time t equals 0, you're going to get this. If you measure a millisecond later, you're going to get this. If you measure a nanosecond later, you're going to get this. It's a kind of a program. And the program is shared between these two particles, so that this particle will give you always the complement result of this particle. Right? I think this is very intuitive. Who would not think that this is the case? Maybe Niels Bohr. If you are not Niels Bohr, you'll probably think, well, that's what's happening. That's the explanation. Obviously, quantum mechanics appear random to us because we don't have access to this program. Yeah.
Are you saying that, like, they're pre-programmed to always just do the opposite in time?
Yeah, they carry their own programs, and their programs are set up so that they will.
Wouldn't it make more sense, though, that one of them being the other state would just affect the other one to go, or like they...
Aha! Aha! Very good question. All right. Very good question. Good. Yes, it is plausible until there is a paper. 1926? No, 1930? I forget. But it's such a famous paper that it is in public domain. So you can access it in a Project Euclid, anywhere in the world, no affiliation to any university required, by Einstein, Podolsky, and Rosen. So famous, it's called the EPR paper. The EPR paper. The title of this paper is, Can the Quantum Mechanics Description of Reality be Considered Complete? That's the title of the paper. But it's not a philosophical paper. They define what it means to be complete. They did.
What did you say it's called?
Can the quantum mechanics description of reality be considered complete? Eisenhut also. EPR paper. If you just Google EPR paper, you'll find it. It's that simple, extremely famous. Question? No? So that's the argument. But maybe that's it. Maybe that's what Jackson said. Maybe they don't need to carry programs at all. Maybe they just send a signal and say, well, I measured spin up, you'd better be spin down. But the problem that you face with this is, how do you explain if you have space-like type of measurements? If the measurement on the event of measuring one of the sparks was space-like separated to that, there is no way to have communicated. And nonetheless, the prediction is unequivocal. If you measure, you should obtain the opposite. Now, perhaps this is a good exercise before we can do, yeah, let's do this now. Oh, yeah, let's do it now. Let's see what happens in the probability solution. So let's rule out faster than light communication immediately, regardless of what quantum mechanics says, regardless of this program or no program. Either way, you can't have faster than light communication. Let's see how. Let's see this now. Let's see. So that's called selective versus non-selective. So you see in the literature people talking about selective versus non-selective measurements. Oh. S comes after T. So let's say that your state is B3. The global state is B3. Well, let's see. And Alice makes a measurement on her particle. So, and we are bottom. We are all bottom. We are space-like separated from Alice. So we can't communicate with her. And two possibilities. Either Alice made a measurement or she didn't. If she didn't make a measurement, let's find the probability of finding the state up and state down. We know that the state is B3 prior to measurement. We prepared that and then we know that's the case. Well, the probability we'll see by just looking at the projections. Right? So the projections of this state on up. So let's apply that to the projection once, 1 on Alice times up, up. Okay. Well, the resulting state will be 1 root 2 on up. So the eigenvalue of the probability is 1/2. I can do the same with down, down. And the probability will be 1/2. Well, there are only two possible outcomes, so the probability should be equal anyway. Well, if 1 is 1/2. There has to be 1 minus that one. So this is if Alice doesn't measure. If Alice does measure, what's the probability I measure spin up? But I don't know the result because Alice is space-like separated from me. So I have to use the rules of probability. What are the rules of probabilities? Well, the probability I measured spin up, given that Alice measured up, plus the probability of measuring up, given that the Alice measured down. Conditional probabilities. That's the rules of probabilities. If Alice measured up, what is my state? My state is down, necessarily. If Alice made, so this is 0. if Alice may, times the probability of Alice up times the probability of Alice down. So this is 0, right? What is this? Well, if she measured down, my probability of measuring up is 1. But it times the probability of Alice measuring down, which is 1/2. So this is 1/2 again. And obviously the same, well, 1 minus the 1/2 is still 1/2. So the probabilities don't change. So this is a very concrete example on this state B3. And actually this could be a nice homework problem. Prove that in general, for every state. You use that density matrix reduction, you find the reduced density matrix and prove that the density, that the probabilities are there. And this is called a non-selective measurement. Now this is very different. If Alice calls me and say, oh, I measured up, then I change my probabilities because I remove one of these factors. Then I make a better prediction. My probabilities won't be equipartite. Won't be 1/2 or 1/2. It'll be 1 and 0. It's a much better prediction. But I need to have knowledge of Alice's result to do that. And that's called a selective measurement. So, but now if you play this following game, if you play the game that you are outside of the universe, so you don't live in space-time, but you were just watching, like someone outside of the universe. So that's why the interpretations and violations of that Gauss inequalities become debated. Everyone loves Gauss inequalities. They might disagree what they mean. Well, they don't disagree. Okay. They might disagree about how to interpret quantum mechanics in general, but everyone will love Gauss inequalities. If you play that game, you say, well, I know from the outside of the universe, I have knowledge of both Alice and Bob, so I should be able to make these better predictions. But if you can make these better predictions, how to explain that you don't observe faster than light communication? So that argument, Einstein, Podolsky, and Rosen, and I misspelled Einstein. That's terribly misspelled. Okay, my goodness. Einstein, Podolsky, and Rosen, they don't talk about this part of life. They kind of implicitly assume that this is impossible, and they are trying to say, well, the quantum mechanics should be able to do this outside of the universe predictions, and they are not allowing us to. So they conclude that the quantum mechanical description of reality cannot be considered complete. So with that in mind, I think for most people this programming is the most natural option for quantum mechanics. Well, that's not the case, and we are going to prove it on Monday. See you then.